Here it is. Okay, Teoría de la Computación, Theory of Computation. So the basics here, important basics are related to notation. Sometimes other books use a different notation. So we will consider uppercase letters to denote sets. So this is a set called A, un conjunto llamado A, which has elements, and usually the elements of this set will be given in lowercase, en minúsculas. Entonces el conjunto en mayúsculas, los elementos en minúsculas. Esto es como convención. This is a convention. And also, it is possible to have a set made of subsets. Let's say we have A, B, and then C and D. And if we want to count the number of elements a set has, we can use this bar, which represents the number of elements a set has. So this will be how many elements the B set has. So we can count them like this. This is 1, this is 2, and this is 3. Yes, because this one is a composite subset, which is just one element. So the number of elements of B is 3. The number of elements of A is as well 3. Yes. In addition to that, we will have some special sets called N, which is the set of natural numbers, which begins with 0, 1, 2, 2, 3, etc. And this is a convention because some people, I don't know, for example, people coming with a math background, maybe you are used to have natural numbers beginning with 1. So in this case, as a convention for this course, whenever we want natural numbers to begin with 1, we will say, we will add this plus, which means all the positive natural numbers, todos los números enteros positivos. Entonces, cuando tengamos n así solito, vamos a empezar desde 0. Eso es muy importante. Cuando tengamos n más, vamos a empezar desde 1. Para que se acuerden, entonces el más va a representar todos los enteros positivos. Y cuando no tenemos simplemente son todos los no negativos. Okay, so these are two very important conventions we will have during this course. Okay, so if we want to check if an element belongs or not to a set, then we can ask, does C belong to B? And we can say, yes, C belongs to B. With the symbol we have here. C es un elemento, C pertenece a B. And also we can say a composite or a subset like A, B is an element of B as well. You can say these two things. However, we cannot say A belongs to B. Why? Because we have A here that is enclosed inside another set. So this is not true in this case. A does not belong to B, nor B belongs to B. These two are not true. However, it is true for A. If I say A belongs to A, yes. Why? Because we have this part. A belongs to A, B belongs to A, etc. Okay? Good. Then we have the union of two sets. For example, if I want to have the union of these previously defined sets A and B, I will denote by this symbol, which is like a U, a big U. And we will have all the elements that belong to either one set or the other set. Es decir, todos aquellos que pertenecen a un conjunto o que pertenecen al otro conjunto. Entonces tenemos A, B, C, A, B como un elemento. C ya no lo pongo. I will not repeat this C, which is common to A and B. I will not write it again. Why? Because in set theory, I am not allowed to repeat elements. If I have C already, there is no use to add it again. No se repiten los elementos en un conjunto. Also, very importantly, the order of the elements inside a set is not important. So I can say, for example, C, B, A, B, D, or even I can begin with A, B, and then D, A, B, C. It's exactly the same thing. And also I can swap the elements inside a subset like B, A, D, A, B, C. So as you can see, all these are completely equivalent, are exactly the same ways of writing this set, which is the union of A and B. Okay? How are we doing so far? So now you have to think mathematically and in English at the same time. I think English is not the mother language of all of us. So if it's hard, please tell me, don't worry. But I think so far concepts are not so difficult. Yes? Okay. And now let's see the intersection. So this is union of two sets. Intersection in English, or intersección in Spanish, it will be denoted by A, and it's like an inverse U, looking downwards, A intersection B. And now we have to consider all those elements that are common to both sets. In this case, we have only one element, which is C, that is common to the two sets. So on purpose, I have written this subset here so that you are conscious at all time that A and B cannot be taken out of this bag. You can imagine sets as bags. And if I have A and B inside this bag, I cannot open the bag to work directly with the element in it. So I cannot say A and B are common to this set and this set. Why? Because this is just a bag. Seen from the outside, I see only a bag, and then C and D, and here A and C. So C will be the only element which is common to both languages, to both sets. Sorry. So we write it like this. This is very important because sometimes when we are beginners, we tend to write, oh, it's only one element, then I can write it like that. No, please don't do like that, because always the union and intersection of sets gives as a result a set. And I need to use these curly braces in order to represent this is a set. So in this case, I will say, no, don't do this, okay? This is not correct. It's not the same. It's not the same to say this is an element and than to say this is a set. Okay, I will change page of my whiteboard, which actually is a yellow board. Okay, subsets. Maybe I need to recall this subset, these sets from here. So I will take this And using the advantage of technology, I will do this. I can do this in the classroom, so there are some advantages to lecture like this. Okay, ABC, the same sets we have here. Now, I can say A, B, as a set is a subset of B. So this will be represent subset. I can use bags in order to say that some groups of elements are form a subset of another set. For example, I can say as well, C, D is a subset of B, or even just one element, a subset of just one element. Oh my God, I have run out of battery of my pencil. Okay, so we have to wait 2 hours for it to recharge. Now, in 5 minutes, it's ready. So I was going to write D and then close the curly brace is a subset of B. Please observe that, let me see if I can point with, yeah, I can point with my finger. So let me try to finish this. No, I cannot finish with my finger. No. No, but I can point. So here, I close this curly brace. Curly brace es paréntesis. Además, ¿cómo se dice? La llave, es una llave. A curly brace es una llave. It's a subset of B. Please observe the curly braces always, here, always, always. Why? Because whenever I speak of a subset, I need a set on the left side. So I cannot write D without the curly braces. D is a subset of B. Yes, I cannot say that because always I need to speak about a set on the left side. So this symbol, which means subset, is always working with sets on both sides. On the left side is a set, on the right side is a set. And also, this symbol we see here is called proper subset. A proper subset cannot be exactly the same as the set itself. I mean, B cannot be a proper set of B. However, the definition of subset is with a little symbol here, which would mean that B can be a subset of itself. So this is a bit difficult to understand. Moreover, if I'm not drawing anything, I'm sorry, but I will explain again once my pencil is a little bit charged. Let me see how much charge do I have so far. So can you see this I'm doing? Yes, right? So if I receive a strange message or something, you will see it. Okay, no problem. We are in confidence. Okay. So let me see if I have at least a little bit more of power. Okay, now I will repeat this now in Spanish. Tenemos aquí este operador que se llama subconjunto de un conjunto. Entonces, siempre que decimos que es un subconjunto, vamos a estar utilizando llaves. Observen que del lado izquierdo siempre hay llaves. Esto quiere decir que es un subconjunto tanto del lado izquierdo, pero no es un conjunto, tanto del lado izquierdo como del lado derecho. Entonces, lo que no podemos decir es algo así como esto. Esto es incorrecto, ¿sí? ¿Por qué? Porque de este lado no tenemos un conjunto. Entonces, no debemos escribir eso. Ahora, lo que hablábamos del subconjunto propio quiere decir que B no puede ser subconjunto propio de sí mismo. Esto no va a ser verdadero. Lo podemos escribir. Ojo, pongo tache, pero lo podemos escribir, solo que no es verdadero. Si queremos que ocurra algo así, tenemos que poner esta rayita de aquí abajo. A esto se le llama subconjunto. Entonces tenemos aquí algo muy importante, porque en la primaria, bueno, en la secundaria, no sé, a veces se daba en la primaria, ¿no? Para los que ya estamos muy viejitos como yo, de repente nos tocaba que nos enseñaran en la primaria conjuntos. Entonces, esta parte de aquí la veíamos como que es subconjunto. Entonces tenemos que quitarnos esta idea de la cabeza. Esto aquí en este curso se va a llamar subconjunto propio, y este de acá se va a llamar subconjunto. ¿Por qué? Porque el subconjunto siempre va a permitir que sea igual a sí mismo. Todo conjunto es subconjunto de sí mismo. Every set is a subset of itself. Entonces, siempre podemos escribir, we can always write, A is a subset of A. And this will be always true. True, true. And this is correct, but not true. And this is incorrect. Yes? Okay. Another important property, which is the empty set. This is the empty set, and also we can write it like this. Sometimes also in elementary school, some teachers write something like this and saying, this is the empty set. Well, no, this is a set containing a subset, which is in turn the empty set. So these two are not the same as this one. So please don't get confused on this. No? So I would say this is not the same. You can write this, and well, this is correct if you want to express a set that has one set, and this set is the empty set. You can do this, and then this will be something like writing this. Es como si tenemos una bolsa vacía dentro de otra bolsa vacía, y al final no hay nada, pero todos son puras bolsas. ¿Ok? Pero se vale, ¿no? Pero no es lo mismo que lo de arriba. Arriba tienes una sola bolsa. Sin nada, abajo tienes dos bolsas, una dentro de otra, y no tienen nada al final. So both are correct, just they mean different things. Now, the empty set is a subset of any set. So I can say the empty set, the empty set is a subset of A, the empty set is a subset of B, and also we can write this. So the difference between these and these symbols is just that this one allows the subset to be exactly the same as the set. But in general, it means subset. This is a proper subset, and this is subset. In general, when we speak about subset, we will be thinking of this one. Okay, now we will see an important or interesting operation, because it will allow us to create more different subsets or more different sets. I will change page. Can I change page of this? Which is the equivalent? Can I erase the blackboard? ¿Puedo borrar el pizarrón? Okay.
Sí, gracias.
So now let's recall our, it's not longer on, let me see. Yes, it's still here. Okay, so we paste again. And now I will define another set, which is called C, and the elements it has is D and E. Now, we have the Cartesian product of two sets. Let me arrange this so it doesn't look as a subset, it's a C. So a Cartesian product C, in Spanish it's called producto cartesiano. el producto cartesiano de dos conjuntos A cruz C nos va a dar la combinación de todos los elementos que los componen generando tuplas. So this will produce an ordered tuple which consists of one element of the first set, A in this case, and one element of the second set, which is D. Yes, we are taking this and this. Then we'll take this and this, then this and this, this and this, this and this and this. Okay, we will write them so it's clear. So A and D, then A and E, B and D, and B and E, and finally C and D, and C and E. Yes, so an interesting property of this is that always the number of elements we will be obtaining is the product of the cardinality of each one of the original sets. Remember that we have this operator which looks like two bars, which is the cardinality, la cardinalidad in Spanish. La cardinalidad de un conjunto es el número de elementos que lo componen. The cardinality of a set is the number of elements it has. So A has 3 elements and C has 2 elements. So this is easy. Then how is the cardinality of A Cartesian product C? Well, it's easy. It's just the cardinality of A multiplied by the cardinality of C, which, if we substitute, is 3 times 2 is 6. So this will be true for any sets, for any cardinality of sets we have. And we can verify this in our example. Of course, this is not a demonstration, just a verification of a particular problem. We have 1, 2, 3, 4, 5, 6. We have 6 elements. It's very important to note that each one of these tuples, in Spanish, tuplas, each one of these tuples is considered as one element. However, also there is a very important thing. Remember that we said A and D is the same as D and A. Yeah, observe the curly braces. We are speaking here about sets. But for tuples, which are round parentheses, we cannot do that. A and D is very different than D and A. Yes, there are different elements. Aquí hablamos de conjuntos. En conjuntos no importa el orden. A y D es lo mismo que D y A, completamente. Podemos saber que es un conjunto porque son curly braces, son llaves. Pero cuando hablamos de tuplas, tenemos que A y D es un elemento, es una tupla, que no es lo mismo que D y A. Aquí no podemos cambiarlos. This is very important because sometimes we get confused and we tend to think, yeah, I can, the order is not important. Well, when speaking about tuples, yes, order is very important, right? Okay. So we have created here a new set made of tuples, which is the Cartesian product of A and C, producto cartesiano. Okay, also we can create a Cartesian product of a set with itself. So what about saying A, no. Sorry, A cross A. Well, then we have, can you tell me how many elements will this set have?
9.
Yeah.
A
right.
to the power of 2.
Yes. So we have A, B, AC, and you don't have to use a second row for this, but no, I'm wrong. It's BA, BA, BB, BC, and CA, CB, and C, C. You can list all of them just in a single row, but I'm writing in 3 rows so that you can see that I am how's the combination being created. Okay, so we have here again that the cardinality of this will be A multiplied by the cardinality of A, which is 3 times 3, which is 9, which of course it's true, what you have already said. And also we can observe that this is the same as 3 to the power of 2, as Rudenko said. We will go on further to this formula. So we can also extend the notion of Cartesian product to speak about sorry, I can do something like this, C cross C, and then add another one. So now you start thinking, what will happen when I do this? If I do this, then I will have tuples of 3 elements instead of 2. So if I do this, I will have something like D, then the E, the E, the E, 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 the E, the E, sorry, it's a bit confusing. You can help me if I get stuck. E, V, and I think finally E. I'm not sure if I have already finished. Let's count. By the formula, this should be 2 times 2 times 2, which is 2 to the power of 3, should be 8 elements. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay, then I think I'm done. Okay, so this will generate tuples of 3 sub-elements, unas trituplas o tuplas de 3 elementos, ¿no? Tripletas también se llaman en español. En inglés quizás triples. En general, cuando decimos tupla o tuple, es de cualquier tamaño. Incluso podemos hablar de K-tupla, ¿no? K-tuple. Una K-tupla es de K elementos, porque así como vemos, podemos extender esta noción a tuplas de 2 elementos, de 3, de 100, de los que ustedes quieran, siempre y cuando sea finito. Okay, then also to represent this these Cartesian products of the set with itself, we will be using this notation here, A squared, and also here C 3, like to the cube. However, this is very different than this operation. Here we have a power operation, 2 to the power of 3, and this is very different to this 3 here. Just be aware that although they are related, whenever we are speaking of sets here, we will mean a Cartesian product. Yes, C is a set, and then C to the power of 3, or C upper script 3 will mean this, and while a 3 here means a power, right? Okay, don't sleep, just one more concept to go. Well, a couple of concepts yet. So I will change page here. If you need some time that if you are taking notes or something and I'm changing page so fast, you can tell me and I will go back. Okay, so another important, let me see, let's recover C, which was D and E, right? Is this correct? Is the same one as before? Yeah. Okay, now we have another operation which is called the power set of a set. So the power set of C consists of all the possible subsets I can build from the original set. So if the original set is C, I can build the empty set Remember that always the empty set is a subset of any set. And then I will begin listing those subsets that consist of one element, which is D, and then E. And then I will list those subsets consisting of two elements, which is D and E. Remember that DE can be a subset of C, the subset itself, which is, as I expressed before, C. C is a subset of C. This is possible, then it's possible that this part here, DE, is a subset of a possible subset of C. And that's all. There are no more subsets possible from the original subset. Then the power set of C is this one here. El conjunto potencia, the power set. El conjunto potencia de C va a estar conformado por todos aquellos subconjuntos que pueden obtenerse a partir del conjunto original. El conjunto original es C. Entonces recordemos que el conjunto vacío siempre es subconjunto de cualquier conjunto. Entonces empezamos por ese. O podemos pensar todos los subconjuntos formados por 0 elementos, todos los subconjuntos formados por un elemento y todos los subconjuntos formados por 2 elementos. Como DE es exactamente el mismo, sí se vale, ¿no? Por eso puse esto de acá. C es un subconjunto de sí mismo, aunque, perdón, debe haber escrito así. Ahora sí, C es un subconjunto de sí mismo, ¿no? Si no estoy diciendo que es propio y justamente dije que eso no se hace, ¿no? Ok. Puedo hacerlos más bolas diciendo que es propio y dije que escribir así no es propio, pero ya, eso es para hacerlos bolas, a propósito. Muy bien. Entonces, tenemos aquí el conjunto potencia de C y vamos a calcular ahora el de A. Para A, que era A, B, C. Right? Just to remember, okay, A, B, C. The power set of A, I always remember there was a teacher, maybe Sarah remembers him, that used to teach us about the Fourier transform. So the Fourier transform is represented by a curly F, but this teacher said it was in Spanish una F cachonda, a hot F, because the F was hot, so it was doing like this. So whenever I explain this about the power set, I think, okay, this is a hot P or something like that. Okay, give me a second. There is something sounding over there. Okay, it was a very old 3GS iPhone, so that I just put it to charge and it had the alarm sounding. Okay, sorry for the interruption. However, the concept of the F cachonda is older than the iPhone 3G. Okay, so jokes apart. So we have a curly P, and this curly P is, if we take the curly P, the power set of A, then we have, again, the set formed by all those subsets with 0 elements, which it's only one, those formed by 2 elements, which are A and then B and then C, and then those by 2 elements, combination of 2 elements, so we have A and B. We will not have B and A. Why? Because we won't allow repetition in sets. So AB, AC, of course, we don't have AA as well, but we do have BC, and I think that's it for the set of 2 elements. Then what about the set of 3 elements? Well, we have only one, A, B, C. And now the question, am I done? Did I miss any of the possible subsets? Well, there is a formula to know this. And this formula is the following one, is that the cardinality of the power set of any set, let's write X, is exactly 2 to the power of the cardinality of the original set, which is, in this case, X. So if we try to measure for our examples here, we can say that the cardinality of C is 2, the cardinality of A is 3. For this one, then my power set should be, the cardinality of the power set of C should be 2 to the power of 2. And this is 4, which is consistent with what we obtained here. Again, this is not a demonstration by any means, but just an application of this formula. And for the second example, we have, what about this? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 elements. So apparently the cardinality of PA is 8. Let's see if it's consistent with this formula. So it should be 2 to the original cardinality, which is 3. My God, this is wrong. A is 3. So this should be 2 to the cardinality, to the power of the cardinality of A, 2 to the third power should be 8. Okay, right. We are doing it right. So this is very important. I mean, is maybe for our mathematician friends is not new at all. However, this will be an important basis to say what can be computable and what will not be computable, and we will see why. It results that now we will have different sizes of infinite sets. First, let me introduce you the concept of infinite, finite, and infinite. This seems to be relatively easy. Finite is something that we start counting and we will finish counting at some point. For example, the number of people in this room, this is finite. The number of, I don't know, the number of Mexicans in Mexico, it's finite. The number of Russians in Russia, the number of Ukrainians in Ukraine, those are finite numbers, right? And however, even some things that are very difficult to count are finite. For example, the number of grains in the planet Earth. My God, how many? We don't know, but it's finite. And the number of hairs on our scalp is finite. There are so many, we cannot count them easily, but it's finite, okay? So what about infinite sets? Infinite sets are those that we will never be able to finish counting. So for example, the number of natural numbers. Remember that n represented for us the natural numbers beginning with 0, because I'm not adding this. So this is the number of natural numbers. So if I ask what is the cardinality of this, well, this is infinite. Okay, now it results that there are more that are even bigger or different sizes of infinite sets. One of these is the power set operation. Why? Because if I do, or if I want to calculate the power set of the natural numbers, which is terrible because I'm trying to calculate the power set of an already enormous or huge set, we will have that the cardinality of this is something like this, 2 to the cardinality of natural numbers, which is something like 2 to the to infinite power. And we know that this is a much greater quantity than infinite itself. So we can say that this size or this dimension is even a bigger kind of infinite. This is called uncountable infinite. Why? Because, Rudenko, please.
I wanted to ask it, is this the same uncountable, like, is this the same cardinality as like the cardinality of real numbers, for example?
Yes.
Because there are different cardinalities for natural numbers and real numbers, for example. So
Good
this
question.
is.
Yes, in terms of the categories of infinite, we could be speaking of Aleph 1. So this is, there is another notation for calling or speaking on this. The first infinite, which is this, is called, let me see if I can draw it properly. It's something like this. This letter is the Hebrew letter called Aleph, like the novel by Jorge Luis Borges, El Aleph. So this is una letra hebrea que se llama Aleph, así se llama. No sé si la dibujo bien porque no sé hebreo, pero intento. I try to write the Aleph letter. So this is Aleph 0, yes, the first infinite. Then the second bigger infinite is called Aleph 1. So this cardinality would be Aleph 1. And because I can do something really, really weird, such as the power set of the natural numbers, if I want to measure the cardinality of this, then this would be, I think it's something like this, Aleph 2. Aleph 0. Aleph 1, Aleph 2, etc. You can see there is an infinite number of infinite categories. Yeah, well, this is so crazy, but we can imagine crazy things when doing math. So usually I don't speak too much about this notation, Aleph 0, Aleph 1, because we will be concentrating in this course only on the first two, which are Aleph 0 and Aleph 1. Son los dos tamaños de infinito que más nos interesan. Hasta aquí, este va a ser infinito contable. Y ahorita vemos por qué es contable. Y este de acá es infinito incontable. Y la pregunta de Rudenko, do you prefer to call you Rudenko or Dimitri or Dima?
You can call me Dima. It's like,
okay.
It's how people usually call me.
Okay, very good. So, la pregunta de Dima era que si la cardinalidad de los números reales es mayor o menor o cómo queda con respecto a esta. Ahorita más adelante vamos a entrar a explicar esta parte. ¿Por qué es el primer infinito incontable? ¿Por qué no la cardinalidad de los números reales está acá o acá, etcétera? Vamos para allá. We are going to that. Meanwhile, we have to understand that the smallest set of infinite is the cardinality of the natural numbers. And the second biggest one is the power set of the natural numbers. And this yields an uncountable infinite. And from there, we can create a hierarchy of infinites. Yeah, so that's why this class is a bit like the meme says, like, because it makes you think about infinite sizes and empty sets and a lot of empty bags containing nothing, but they are something, etc. Right? But you can use it for meditation as well. Okay, so now we say this is uncountable. Why? Because in the first case, we can try to align any element to one element of the natural numbers. So this is why this is the smallest infinite the smallest infinite, possible infinite. Why? Because if I have something that, even if it's infinite, I can always map 1 to 1. I mean, I can start counting 1, 2, 3, 4, 5, 6, 7, 8. And I will never finish, but always there is a mapping, a direct mapping between these numbers and the infinite numbers. So let's see what happens, for example, with A cross A, with the Cartesian product of something like this. A cross A, well, it's not interesting, but what about N cross N? So do you think this is infinite? Well, this is infinite for sure, right? So, but this is infinite, is countable or uncountable? What do you think? Feel your intuition.
And if I know the answer.
That no answer?
Yeah, I know the answer.
Okay. Now, if you already know, then don't say that. But let's try to solve it by intuition. If someone, for example, the way of trying to think about this is, okay, I have something like the cardinality of this set is something like the cardinality of each one of the sets composing it. So I have something like infinite times infinite. So is this, in this case, is this quantity much larger than the original infinite itself? It's going to this place. The question is going to this place. So this is question. I'm not saying yes or not. What do you think?
I think that it's uncountable because, as you said previously, when we have two Cartesian product, we need to have subsets, elements that form a subset.
Yeah.
So if there is infinite, the real numbers are infinite. I think that we will have an abstract concept like infinite. I am not sure if there is a possible, but I think that is uncountable.
Yes, well, that reasoning is what we tend to think on the beginning. So that's why I asked you. And yeah, I think most of the times we tend to think like that, because we say, okay, I start doing something like 0, 0, 0, 1, 0, 2, etc. Then we tend to think we have a growing way here, and also we have 1, 0, 1, 1, etc. And also we have an infinite growing in this direction. So it seems to be that I cannot count them. However, there is a trick to be able to count this. And if we can count it, then it's countable. So the trick is, okay, let's group them by their sum, por su suma, which is, first, let's count all of those elements whose sub-elements yield 0. So we have, for those giving 0, is like this. Now let's count those giving 1, which is 0, 1 and 1, now let's add up those giving 2, 0, 2, 0, 1, 1, and I think that's it. And now you see where I'm heading to. And now we have 3, like this, yeah, 3, 0, and also we have 2, 1, and 1, 2, and that's it, etc. So the important thing to note here is that on every step, I am being able to find a finite set for 0, a finite set for 1, a finite set for 2, a finite set for 3. And you can see that if I continue doing this, I will always have a finite set corresponding to a natural number. Then I'm being able to count them. Yes, so this set is infinite. So in this case, we can say that that no, it's not that bigger. So we could say something that I don't know if I will abuse of the notation, but something like this, that it doesn't matter if I'm doing the dot product of infinite numbers, I remain on the same dimension of infinite. So all the Cartesian products, even if I do it many, many times, like, like this, and this, and this, and this, even so, this is countable infinite. Why? Because I will be able always to apply this trick. And the important part of this trick is that I am being able to count in some way. I am arranging the elements in some way that for every natural number corresponds a finite set. If this would be infinite, then I'm in trouble, which will be the case for other sets. Now let me present one of those, which has to do precisely with the real numbers. The real numbers, which are represented by this special notation R, are those numbers that can be infinitely precise, which means that I can add as many zeros as I want and add this number. Then I can think of a smaller one, like just adding, I know I didn't count the zeros, but suppose it has just one more zero, yeah? So the problem with this is, if I want to apply the same trick as before, which consisted on arranging the numbers on such a way that I can map them to the natural numbers, then I can try to count from 0 to 1, let's say, in real numbers. Then I say, okay, from 0 to 1, how many numbers do we have? How many real numbers are there from 0 to 1? ¿Cuántos números reales hay entre 0 y 1?
More than natural numbers.
Yeah, right. Right, because if I try to count, okay, well, 1, I don't know, maybe, okay, let's change the question from 0 to 0.1. No, let's change the question. First, we have to count from 0 to 0.101. No, let's change the question. So you can see where are we going to. So even if I change and change and change the question, I cannot even count up to 1, and I'm deep in an infinite level of numbers. Yes. So in this case, yes, we do have like 2 dimensions of infinite, because I cannot even pass from 0 to 1, and also I have from 1 to 2, etc. So this kind of real numbers is an uncountable infinite set. Es infinito incontable, porque no puedo hacer un mapping, no puedo hacer un mapeo entre los números naturales y los números reales. Y esto se pone también como que la cardinalidad de los números reales es mucho mayor que la cardinalidad de los números naturales. And there are other demonstrations which show why this is Aleph 1, why this is equivalent to the cardinality of the power set of the natural numbers.
Sorry, I have a question.
Yes, please.
So in this case, the real numbers is use uncountable infinites in all of the operations. I mean that for example, I can multiply a real number plus real number. It's an uncountable infinite. Yeah.
Well, we are speaking on the total set. Well, maybe what you're asking is that if you multiply, let's say, if there is a number A, which belongs to real numbers, and another number, let's say B, belonging to the real numbers, if you multiply A times B, will this result be a real number? This is the question.
Yeah.
Well, yes, in particular for this case, yes, real numbers are closed under the operation of multiplication. Yes, you are still in the realm of real numbers, but we cannot say specifically that this is infinite uncountable, or this, because we are speaking about particular numbers. Let's say if we put 0.5 and 0.7, which are real numbers. And if you multiply them, it will yield 0.35. And yes, of course, this is a real number. But these numbers themselves are not infinite uncountable. I don't know if I understand your question properly.
Okay, yeah, it's yes. the question, the answer.
Yes, and I will repeat this in Spanish because it's very important. Cuando hacemos una operación dentro de un conjunto, donde cada uno de los elementos pertenecen al mismo conjunto, nos preguntamos si el resultado va a caer dentro del mismo conjunto. Por ejemplo, si quizás en la división, si tenemos una división entre dos números naturales, 5 entre 2, ¿no? 5 entre 2, y 5 pertenece a los números naturales, 2 pertenece a los números naturales, pero el resultado, 2.5, no es un número natural. Entonces decimos que la división no es una operación cerrada dentro del conjunto de los números naturales. Division is not a closed operation under the realm of natural numbers, because result yields us a real number, yeah, or a fractional number, but it's real anyway. But if we consider this is real and this is real, well, then it is closed. So to mean that an operation is closed, que una operación es cerrada, that operation is closed under some set, is a very important concept that we will be using next. The question of Emilio is important in this sense because he is wondering what happens if I do a multiplication of any pair of real numbers. Will this be a real number as well? Yes, the answer is yes. The real numbers are closed under the operation of multiplication. Okay, so that now that I have filled your head with different sizes of infinite numbers, now we can think of the computability of some functions. Let me add a little bit of more explanation. We have a function. We will call it f. F is a function. A function has a domain and a counter domain. En Spanish, dominio y contradominio. Eso creo que también ya lo vimos en la primaria, secundaria o prepa. Bueno, ya lo vimos en algún momento, ¿no? Entonces, una función tiene un dominio y tiene un contradominio. De tal manera que si nosotros decimos f de 5 y mi f es igual a, digamos, f de x es igual a 3 por x, entonces f de 5 va a ser 3 por 5, 15. El dominio de esta función, pensando en números naturales, puede ser de los números naturales y el resultado da en los números naturales, ¿no? También podemos tener funciones que llevan dos argumentos. We can have functions with two arguments, for example, x, y, and then have a result depending on both, maybe x plus y, and then this can be, the domain will be the Cartesian product of cross n, and the result will be just a natural number. Yeah, so my domain is this one and counter domain is this one for this kind of function. So we can have a lot of different functions. Okay, now let's imagine we have a function whose domain are natural numbers, and the counter domain is only like a Boolean number, un número booleano, meaning it can be only 0 or 1, just like. It means that if I tabulate this function, I can have here some x, which is my input, my domain, x belonging to the natural numbers, and here we will have some result. So as x is on the realm of natural numbers, we can think of something like this. Of course, this is infinite, right? because it's defined on the natural numbers. Then the result can be 0 of 1. Maybe I can say, okay, let's turn on a little bulb. Vamos a prender un foquito whenever there is an uneven number, an odd number. Something like this. You see the idea here. Let's suppose there's a function that says yes whenever the input number is odd. Okay, now how if I say no whenever it's, let's not erase, whenever it's even? Well, for 0 is not an odd or even, so it will be like this, like this, like this, etc. How about a function that says yes when any number is less than 3? It'll be like this, and then 0 for all the rest of the numbers. Okay, now let's make a function that detects all those prime numbers. Okay, so 2 is prime, 3, 5, 7, and so on. Function for detecting prime numbers, para detectar números primos. So what other function do you can think about? Tell me another function, please.
Function that equals 1 when the x equals 0, for example, and all others the zeros.
And zeros, yeah, that's another function. Okay, Dima. And another one. We are just inventing arbitrary functions for the sake of having fun.
If the value is greater than 5, we can make the value 1.
Okay, if it's greater than 5, the value is 1. Okay, very good. Well, etc. We can spend all the evening together inventing functions, and we will never finish doing this. Yes, it's very fun, however. We can spend a lot of time doing this. What I want you to see is that we can invent so many different functions. The question is, how many different functions can be invented that have this form from n to 0, 1? How many functions of this kind can be defined? Good question, Nathan. Then there is a way to calculate this, and we already know this. The way to calculate this is considering that every time I select a 1 here, it's equivalent as if I select a number here. Then for all those having a 1 there, then I just make a new set. So the result will be the new set formed by 1, 3, 5, 7, 9, and etc. Then this function here is defining a set. This function here is defining another set, which is 2, 4, 6, 8, 10, etc. Then we have transformed our question from how many functions can I define on this way to how many subsets can I calculate on n? How many subsets can be obtained from n? And today we have seen a way to calculate this, because this is exactly the same question as what is the cardinality of the power set of n. It's exactly the same question. So to answer how many functions can I build on this fashion, it's exactly the same question on how many subsets can be obtained from a set, right? And this is the cardinality of the power set of n. Well, we know the answer. This is on the It's approximately 2 to the infinite power. But we have a problem here, because this number, well, we don't know it's a problem yet, but it will be a problem, because this number we know it's infinite uncountable. Well, uncountable infinite. Okay, so to finish this class, let's just pose a last question. Given any programming language, how many different programs do you think we can build? Is that, considering there is no memory limit, there is no storage limit, let's think on the ideal computer or theoretical computer. How many different programs could I write in any language? You can think on Z, on Java, I don't know, your favorite language, yes? So there's a way to count this as well. To count this, we will apply exactly the same trick we applied here. We will group the programs with 1 instruction. We will group the programs with 2 instructions, with 3 instructions, etc. The programs with 1 instruction will consist on just 1 keyword, print, or clear screen, I don't know, maybe if and for are not suitable because they need more arguments, but maybe you can include here. And the important part here, as well as when we count it here, is that we have a finite set of programs that we can build, yes, with 1 instruction. What about 2? Well, there is a finite set of programs that I can write with 2 instructions, right? With 3, again, finite. With 4, finite. Always will be finite. However, yes, you can tell me, yes, the number of programs I can write is infinite. But if we group them, every set is finite, which has a very interesting consequence, that the number of programs we can write using any language, computer language, is infinite, but it's countable. But the number of functions we can define, mathematically define, is infinite uncountable. Then, oh my God, there are more functions that I cannot calculate than those for which I can build a program. So this is the essence of this course, the things that are not computable. Now, in the next sessions, we will see, well, then which ones are those? I want to know, yes? Now we have shown that there are a lot of those things that cannot be computed. And that's why this course is called Theory of Computation, because it's the theory of what can be computed and what cannot be computed and why. Yes? Well, so this is why we needed all these theory set and the infinite sizes and all this to conclude this session with this. So please, in the 4 minutes, we have questions. Or thoughts. You can say, wow, I never imagined. I always thought that Java was the most powerful language in my life. And now I see I cannot implement everything.
It's pretty curious to know what are these problems that could not be computed.
There are more programs that can, well, not programs, there are more functions that cannot be computed.
Yeah.
For which there is no program at all.
Could be similar as an example of problems P or INIP problems?
No, that's a complexity issue. And by the end of this course, I hope we have enough time. The problem will be that, okay, it's computable. Once we find it's computable, but guess what? I will give you your result in 23 years. No, in 5 million years. Well, then that's an NP problem, because the NP means non-polynomial. That cannot be solved in polynomial time. So it's a problem of complexity. Both P and NP are computable, but NP is highly complex, whereas P tends to be more decent.
Okay, it's more for the complexity of the algorithm. Yeah.
Yes, right. Very good question. Because sometimes we try to, sometimes we get confused with NP, which means no se puede, no? NP, no se puede. Cannot be, but no, don't learn that. Okay, so now we have finished our chapter 0. So remember what we said about each chapter, the finish of each chapter, what we said. What happens at the end of each chapter?
There's an exam.
Yeah, right. So you will see, oh man, how aggressive is this professor. After the first session, there's an exam. Well, yes. However, this is more like a, how to say, examen piloto, like a trial. No, like a
Demo.
Demo, yeah, demo. I like demo. A demo exam. So next class, Tuesday, there will be an exam regarding all these basic topics. For this, you can check the chapter 0, the exercises at the end of chapter 0, which is, they start at page 17 and finish at the page 20. So give them a look. And next Tuesday, I will open the Moodle system for a short quiz, 10 to 20 questions, which is like a demo exam. How do we, diagnóstico? How can I say that? An examen diagnóstico, like to see in general your math skills. So don't worry too much if you want to have a better result here. However, check the end of the chapter 0. So next Tuesday, I will be here. So please open this session. I want also to see you and interact you while you perform this exam. If you have questions as well, you can ask me through this way. But the exam will be on the Moodle platform. And also, of course, if you still have no access to this Moodle platform, please send me an email so that everyone can participate.